Okay, then let me give a brief introduction about Professor Jian. Professor Jian received master and PhD degree in electrical engineering from the Ohio State University of Columbus in 1987 and 1991. Respectively. She's currently a professor in the Department of Electrical Engineering and Computer Engineering at the University of Florida, Gainesville. Her current research interests include spectral estimation, statistical and array processing, and their applications to radar, sonar, and the biomedical engineering. Dr. Lee's publication includes 4 books. The first one is robust, but that is beamformers, published by Wiley in 2005. Spectral analysis by Morgan 2005. The third book is minor radar signal processing 2009. Wiley. In the waveform design for adaptive sensing system, Cambridge University Press 2011. Dr. Lee is a fellow of IEEE, is a fellow of IEEE, and she's a fellow of European Academy of Sciences. She received a lot of awards. 1994 National Science Foundation Young Investigator Award, in the 1996 Office of Naval Research Young Investigator Award. She was the executive committee member of 2002 IESS. Florida, Florida, 2002. May 2002. She was associate editor at ESPRIT from 1999 to 2005, and the AE of IEEE Signal Processing Magazine from 2003 to 2005, and a member of editorial board of signal processing in the Working Signal Bureau from 2005 to 2007. Okay, she was also a member of the editorial board of IEEE Signal Processing Magazine from 2010 to 2012. She's a co-author of the paper. She has 3 Best Paper Awards. One is also winning the Gary Output Award for the best paper published in IEEE Transaction on Aerospace and Electronic Systems in 2005, and another one is IEEE Transaction Signal Processing Award in 2013. The third one is also IEEE Signal Processing Best Paper Award. And one more, the Best Column Paper Award from IEEE Signal Processing Society, publishing IEEE Signal Processing Magazine. As you can see, it's a glorious achievement. Okay, that's it. Welcome, Professor Lee's speech.
Okay, thank you. Yeah.
Is it too bright, or is because it, what is it?
Okay, it's better. I think I like this. Huh? No.
No?
No.
Okay.
Huh?
Correct.
Oh, I think I like the darker version better.
Okay.
Yeah. I think, yeah.
Is
Right.
that okay?
Yeah. Okay, thank you for coming to my web seminar. And also, I want to thank Professor Chi for his kind invitations. This is my second time to Taiwan. First time was 24 years ago. See, life flies by just like that. Feel like I was here yesterday. I'm here again. I'm so glad I got a chance to visit Taiwan again after 24 years. Okay. So this is the format that's required by IEEE Aerospace Electronic Systems Society. So I have to use this format to give this seminar. Okay. So let's get started. Oh, I want to tell you that in December, I think at the end of 2022, I nominated myself. You can nominate yourself to be an IEEE AESS distinguished lecturer. So I nominated myself, and I asked two other people to write me a reference letter. They are very good. They produced the letter in one day. So I caught the deadline. I made the decision at the last minute, and I got this post. But this being the IEEE AESS distinguished lecturer, I must give two lectures per year, at least 2 lectures per year. Okay, so I'm glad that the first one for 2025 is given here in Taiwan. Thank you. So AESS, I must advertise for AESS, right? Because they pay for the international flight. The covers a lot of areas, right? One of them is radar, because I work on radar signal processing, so I publish in this AESS journals. Okay, AESS has many things, right? As I said, journals, IEEE Transaction on Aerospace and Electronic Systems. A new journal is called IEEE Transaction on Radar Systems. That's kind of new. Another thing is they do a lot of education stuff. This distinguished lecture series is part of that. Okay, so AESS now has. Oops, what did I do? I did something. What did I do? Okay, AESS now has more than 100 titles, lecture titles, because each one can give more than one lectures. Okay, I have 2. One is this one. The other one is called Automotive MIMO Radar. But because Professor Chi is a communications person, I thought that he might like the array processing part better. And also, I think between the 2, I like this one better too. Okay. Oops, what did I do? I keep touching something. Let's see, what happened? Huh? Lecture, no, why did it, what's happening? Let me see. This? No. Maybe that's the right one? Anyway, 2023 is the 50th anniversary for this society, AESS society. Actually, 2023 is also my 30th year with University of Florida. So I have been with UF for 32 years now. Okay, long time. Let me do this. Okay, so these are the officers for 2023. This list might be outdated because I prepared this seminar, this PPT PowerPoint file 2 years ago. So it's outdated. But anyway, I think she's now the president. She's with the University of Pisa. How many of you have visited the Pisa, Italy before? No? You know, Pisa has a famous thing called the Leaning Tower. You heard about that? Right. Galileo did the experiment, throwing a big ball and small ball through that Leaning Tower. Did you know that rumor said that if you park here, it's free? Anyways, so this is all AESS standard format, right? So as I said, I've been with UF for 32 years now. And the title of this presentation is called Over a Century of Array Signal Processing. And the reason I wanted to give this lecture was partly motivated by a patent by Intel that they received in 2020. Okay, I'm going to talk about that. Okay, let me give you something there at the end of the talk. Let's talk about it. Okay. All right, so this is the bio. I think Dr. Chi already, Professor Chi already went through that. This is the abstract, but you're going to listen to the talk, so I can skip this part, right? So array signal processing, or array processing, started back in 1905, more than 100 years ago. Actually, 120 years ago, right? The notion of phase array was introduced by this guy. He's a German. His name is Karl Braun. Okay? He actually received, it's not well known, he received the Nobel Prize in Physics in 1909. Okay? Shared with someone you know, Marconi. So this guy shared with Marconi in 1909 to get the Nobel Prize. Okay? So in this lecture, you see here, when he received the award, he talked about his work back in 1905. In this lecture, he talks about, he used 3 antennas by adjusting their phase. When you have narrowband signals, it's sinusoid, right? Sinusoid. So for sinusoid, if the phase is the same, they add up, right, coherently. But if the phase is different, what happens? They cancel each other. That's fading in communication, right? So basically, that's what he did. For narrowband signals, you can change the phases. Basically, time delay is phase change. Change the phases so that you can make the signal go toward one direction, adding up coherently. Okay, that's the idea of phase array. But it started more 120 years ago by this guy, the Nobel Laureate. And in good old days, if you want to do something, you have to do what? Experiment, not now, right? Now we just use MATLAB to do some simulations, right? But in old good days, you have to do experiment. So he did this experiment to show, by adjusting phases, he can make the beam pattern look something like this. Okay. So what are the merits and limitations of this Karl Braun's standard beamformer? There are many names for that. Nowadays, people digitize the signal, right? So this beamformer has another name called DBF, digital beamformer. So we can call it Karl Braun beamformer, 1905 beamformer, digital beamformer. We're talking about the same thing, okay? All right, so the beamformer is what? Just change phases, right? So for transmit, you can change the phases so that they go out in one direction, right? For receive, same thing. You change the phases so that you receive the signal from some angle, right? Okay, so phase array idea is this. You have an array of antennas. Okay, these are the outputs of the antennas. You change the weights. Weights is just phase here, so that you change your phase. So this multiplies, the phase is multiplied by that, and then you add it together. This is called array output. Okay, and then for the beamformer, we talk about beam pattern, right? So you fix your phase, and then you look at what happens when my signals. For example, you fix the phase so that it's beaming at 0 degree. But then when your signal coming from other degrees, what happened to this array output, right? That's called beam pattern. Okay. The standard beamformer, this is called standard beamformer, digital beamformer, or Karl Braun beamformer. It has robustness. Why? It just changes phases. Very robust, okay? If you are wrong a little bit, you see, the signal can come through still nicely, right? That's called robust. If your array has calibration error a little bit, it's not going to affect the output like drastically, right? So that's the advantage of Karl Braun, DBF. It's robust. However, it doesn't have very good resolution. For example, for a 10-element array, half wavelength spacing, the resolution, 3 dB resolution is 10 degrees. So 10 elements, 10 degrees. For automotive radar, for autonomous driving, they want to have 1 degree resolution. So what happens? They need to have 100 elements, right? Because it's inversely proportional to the array, to the number of elements, the array size. So imagine if you have a 100 element array, what happens? Every array output needs to have an IQ channel, right? That's all money. It's getting expensive very quickly, right? But anyways, so it doesn't have a good resolution. For example, for automotive radar, they want 1 degree resolution. Okay? So that means you have to have a lot of elements. And also another thing is it has high side lobe level. This peak side lobe level is about minus 13 dB. Okay, that's a standard thing. Okay? High side lobe level also means poor interference rejection capability. Why? You're beaming at 0 degree. If there's an interference that's coming at this angle, it's going to be only attenuated 13 dB. What if your interference is 60 dB, stronger than your desired signal? It's still going to hurt you really badly, right? So these are the good thing is it's robust. So and because it's robust, of course, when you want to use something in practice, you want something to be reliable, right? So because of that robustness, I'm actually a fan of Karl Braun. I'm a fan of Karl Braun. If you have an array processing problem, the first beamformer you should try will always be Braun's beamformer. Why? It's robust. Okay? Try Braun's beamformer and then try other methods to make performance better than your benchmark, which is the bottom line, Braun beamformer. So Braun, is forever very useful. Okay, Braun's work is forever very useful. It's the first step when you deal with array signal processing problem. Okay, but as I said, it has these problems, right? Okay, so in good old days, things don't change very fast. Nowadays, it's like explosion, right? Things change very fast. So in good old days, in 1905, 64 years later, this guy here called Jack Capon, he was working at MIT Lincoln Lab at that time. Okay, he published this seminal paper in 1969. Okay, he's the one who started the era of adaptive arrays. The idea of adaptive arrays, I want to make the weights based on the data. Remember, this is a big data world. Actually, whenever you deal with the experimental system, it's always big data, right? You turn on the system, you have infinite data coming in. Yeah. But anyway, so when your weights depend on the data, it's called the data adaptive beamformer. Okay? So he introduced something called minimum power distortionless adaptive beamformer. This is what started this area. Guess what? This area is still continuing. I still see people publishing papers even today in journals trying to robustify Capon beamformer. Even today, okay? So what's his idea? His idea is this: I want to find W so that the array output power is minimized. Okay? This is covariance matrix. So this is the array output power is minimized. If you do that, Professor Chi is an expert on optimization. If you don't have any constraint, we're in trouble, right? W equals 0 is your best solution. That means you're throwing out your bad guys. You're throwing out a baby with the bath water, right? If W equals 0 means you don't have a desired signal anymore, but you don't have noise anymore. You don't have interference anymore. Everything's gone, yeah? So you have to have a constraint. Constraint is the signal from this angle, desired angle, comes through undistorted. That's the idea, okay? Actually, the Achilles heel, the weak point is this. This beamformer requires this. What's this? It's array covariance matrix. Ensemble average. We don't have ensemble average in practice. For some of your professors doing real things, you don't have infinite amount of data to get this, right? Sometimes you only have one snapshot. Like you're doing autonomous driving, things change, right? As you drive, you only have one snapshot, maybe 3 snapshots at most. What are you going to do? How are you going to get this? That's the biggest problem for Capon beamformer. Okay? So, but anyway, for this one here, the solution is this, very easy. Okay? And the beamformer, if you use this as your weight, your beamformer output power looks like this. All right. In practice, we don't have ensemble average. So what do? We have snapshots, right? Snapshot is array, you know, in any instant, time instant, you take data, that's called snapshot. Another time you take another data, it's snapshots, right? You don't have ensemble average, so you take snapshots. This is called sample covariance matrix. You use R hat to replace the R here, okay, in practice. And that's the problem. That's the problem to all Capon-related beamformers, okay? For all Capon family of beamformers, this is the weakest point. But before I talk about the problems with Capon beamformer, let's talk about an interesting connection. This guy here, Harry Markowitz, he's with university, he was, maybe, I think I can use was. He used to be with University of Chicago. That's a top school, right, in economics. Okay, you know, professors in the area of economics, they can write very mathematical papers. Their papers can be very toxic in mathematics. In 1955, he wrote this paper. The optimization of quadratic functions. Sounds familiar, right? The Capon beamformer is quadratic cost function, subject to linear constraint. The beamformer by Capon is linear constraint too, right? Guess what? What he's doing, the special case, what he's doing is exactly Capon beamformer. As far as math is concerned, he already solved this problem 15 years earlier, right? 1969, 1955, 14 years earlier, right? But anyway, so in 1990, for his work here, he got Nobel Prize in economics. Okay, so his thing is called a portfolio management theory. It's to reduce risk for an expected return. Okay, it's considered the first revolution in Wall Street, and this theory is still the foundation to modern day investment strategy. So you see, Capon beamformer and Markowitz's work are related. Okay, actually, it's a special case of Markowitz's work.
So
as far as
found this special case,
huh?
I mean, you know, Markowitz's work exactly the Capon beamformer formed by someone. Special case.
Oh, when he wrote this paper, you know, remember Capon in 1969, right?
Yeah.
He didn't know that. But in 1965, in this paper, he had more than one linear constraint. He has a bunch. Okay, if you throw away the rest of them, just leave one of them. That's Capon beamformer. So that's why I said it's a special case. Yes.
So the linear constraint beamformer is the general form of this.
Is a special case of. This is more general. So the cost function is the same as Capon, but it has more than one linear constraint, bunch of linear constraints. Okay, if you throw them away, leave one of them only one, it becomes Capon. So Capon is late, and it is also a special case of Markowitz.
It's more general.
This is more general and earlier, but they are in different fields, so they didn't know.
They're very different. One's
economics, the other electrical engineering, yeah. But they're related. Okay. Anyways, so then people like this one, Professor Bagara. Bagara is actually Wen Chi's student. Wen Chi is that famous book, right? Wen Chi is a student of someone called Li, and Li is a student of Norbert Wiener. So that's a Norbert Wiener's academic descendant, actually, Arthur Bagara. Okay, he works on underwater acoustics. So in this paper, for example, he said something like, "Well, in practice, like in my sonar problems, I only have 3 snapshots. You know, in the ocean is always moving, right? You don't have time to collect your snapshots. The ocean is always moving. Okay, when you do autonomous driving, you only want to have 1 snapshot. Yeah? Okay. So, so in practice, you know, this one is replace the true one, but you don't have snapshots. So you see here what I'm trying to say. The Capon beamformer is too sensitive to be used in practice. Truly, the standard Capon beamformer, the original Capon beamformer, it was very exciting, sounds very good. People try to use it, they get it disappointed immediately. Why? The Capon beamformer has a very fatal problem. That is, it can suppress your desired signal. Because you always have calibration error. We are all humans. We cannot calibrate the array perfectly, right? We don't have a lot of snapshots. And then you use standard Capon beamformer, it will kill your desired signal. So it's worse than that's why I said compared to Capon, I'm a fan of who? Karl Braun. It's robust. It's not going to kill your desired signal. It's going to weaken it a little bit, but it's not going to kill it. This one, if you only run a little bit, you get killed. I'm going to explain why. Okay? So anyways, so for Capon family of beamformers, few snapshots is a problem for that family of beamformers. Presence of steering vector errors. We are human, we cannot make perfect arrays, right? That's fatal. And also signals can be correlated or coherent. For communications, Professor Chi is an expert. You know, you have direct path, yeah, you have multipath. These two signals are highly correlated. Yeah. That can kill the Capon beamformer, right? And also, you know, if you don't use uniform linear array, you use a sparse array to improve the spatial resolution. Say you use 10 element, you stretch it, make it sparse, right? Then you can use something called spatial smoothing to deal with snapshot problem. You know, if you have an array, uniform linear array, what you can do is you divide that into subarrays. That's a snapshot, that's a snapshot. You sacrifice your array size for snapshot. You can do that. That's called spatial smoothing, right? You can do that if you have a sparse array, because this subarray and this subarray are different. Yeah? Because sparse, you know, you look like something here, but by the time you move here, it's completely different. You have missing elements, sparse, right? Okay. So one of my beamforming heroes is this guy, Harry Cox. Okay, he's a member. Is he here? Member of the U.S. Academy of Engineering. He's also a member of U.S. Academy of Engineering. Why? Why is he my hero? He's the first one who made the Capon beamformer work in practice. In fact, I can claim that in some of the practical systems, they are probably still using his idea. Robust, he's the one who worked on robust Capon beamformer. He's the one who made it work in practice. People still use it today, probably. That's why he became this. And I talked to him, one of the smartest guys in the world. That's why he's one of my array beamforming heroes, okay? So he's the one, how did he make work? He made the Capon more robust. How? He introduced the notion of norm-constrained weight factor. Okay? Here's a simple cartoon explanation. Okay? Suppose that this A0 is your true steering vector, right? So that in that covariance matrix R, A0 is in it, right? Because that's your from your data. That's your true array steering vector, right? And A is your assumed steering vector. They are a little bit different. Because remember, we don't know exactly what the true steering vector is sometimes, right? Because calibration error, because multipath problems, whatever, yeah? So remember, your W is to minimize the array output power, right? So W, to minimize the array output power, the nice thing for W to do is what? To be orthogonal to A0. Then remember, I minimize the array output power means anything that's not related to A. Remember, only A is protected. The signal WHA is equal to 1, right? Anything not related to steering vector A, I want to minimize. So if you have a signal from A0, W should be orthogonal to that A0 to kill it, right? Remember, minimize the array output power. And because WHA, W and the assumed steering vector must be equal to 1, yeah? WHA must be equal to 1, right? But this angle is almost, is basically 90 degrees, right? Then this angle is almost 90 degrees, right? If you want this to be 1, what happens? It's almost 0 actually. What do? You make W really, really big. So that's what Cox, I'm sure Cox noticed. That is, when your beamformer is trying to kill your desired signal, see, this W will kill this true signal, right? Your signal you want, right? Whenever that happens, because A0 and true A are so close, and you want this to be 1, W is big. So he noticed that, probably. W is big whenever it's trying to kill the desired signal. Okay? And also when W is big, what happened to the noise? W is a norm, right? Noise power is magnified by the norm square of W, right? So noise is magnified and W is big. So basically his solution is very simple. This is his solution. I make W, I will tell my beamformer, W cannot be bigger than delta. So his beamformer is called non-constrained non-constrained Capon beamformer, right? He constrained the weight. Okay, then there are problems. How do you choose delta? Nobody tells you how to choose delta. That's a problem in practice, right? That's a user parameter. So the more user parameter you have in practice, the worse, the harder it is to use, right? You have to play with it. Just like with machine learning, you have to play with your parameters. Deep learning, right? You have to play with your parameters. Here too, you play with your delta, yeah? So that, anyway, let's take a look at this. The solution is called, is this, diagonal loading. Take R, add a diagonal. You see, it's gamma I. So diagonal is added with I. It's called diagonal loading. This gamma is determined from delta. So if you don't know how to choose delta, you don't know how to choose gamma. Right? Okay, so that's his 1973 paper. So after I prepared this set of slides, I sent the slides to Karl Cox. Okay? He's like in his 80s already, I'm sure. Okay, he's a Lockheed Martin fellow. All right. So I don't know. I Googled his Lockheed Martin email, sent it to him. He responded right away. Okay. He's like, who's counting? I've been working on this for half a century. Right. I gave him in 2023. This paper was published in 1973. Of course, he said that. He was, laughing. So. He's very open-minded to, even though he's not young, right? He's very open-minded. He immediately bought the idea of IEEE. Some algorithm I'm going to talk about later. He liked the IEEE idea, okay, right away. If you tell him about compressive sensing, he'll like, go away. He won't listen to you. He never bought the idea of compressive sensing, but he bought the idea I'm going to talk about today, right away, okay? Anyways. So where was I? I gave you all the little stories, right? So basically, he observed probably, my guess, the norm is big, so he constrained that. And then guess what? This gamma becomes a bridge between the 1905 Braun beamformer and the 1969 Capon beamformer. Okay. So when gamma goes to infinity, what happens? When gamma goes to infinity, R is not important anymore. This becomes Karl Braun beamformer. Right? Gamma is a bridge. When gamma is 0, what happens? It's a standard Capon beamformer. Right? So gamma is like in between the two extremes. This is very robust. This is really, really not robust at all. Right? But gamma is like somewhere in between. That's why it's a robust version of that. So if you choose gamma proper in some application, it works. It will be better than this one. Okay, better than this one, more robust than that one. That's why he's an Academy of Engineering member. He has something that works in practice. All right. Okay, so then in practice, how do you choose delta? How do you choose gamma as a user parameter? Okay, people say, oh, I don't know, I just choose gamma to be noise level. Like I estimate the noise power, just replace gamma with noise power. And then they try it, it doesn't work really well. For example, they can say, oh, 2 times the noise power. Usually people play with gamma, okay? But there's no way of knowing how to find an optimal gamma, okay? So this robust adapt beamformer still fails to work well when the desired signal is highly correlated or coherent with another signal, right? Still doesn't work very well when you have few snapshots, right? Like one snapshot. If you have only one snapshot, this R hat you're going to use is just one snapshot. This and times this. The snapshot is only one snapshot. It's a rank 1. Okay. The sample covariance matrix for this one, if you have only one snapshot, is only rank 1. You need a huge gamma, right, to make it work. When gamma is big, what happens? It's DBF. It's 1905 again. So it doesn't work very well when you don't have a lot of snapshots, right? Okay, another interesting person is this one. You communication people, read Solomon code, right? You know, one of the jokes he likes to say is, I got my PhD from Caltech in mathematics because I failed to get into their physics program. Caltech's physics program is really famous, full of the Nobel Prize winners. Okay, but anyway, so that tells you his background, right? He has a math degree from Caltech, okay? And he's a legendary person, okay? He also worked at MIT Lincoln Lab a little bit, okay? And he published this seminal paper in 1974, okay? See here, first author, right? Rapid conversion in adaptive arrays. So at that time, adaptive array was just getting hot, right? So what is he doing? He's looking at the space-time adaptive processing for wide area surveillance. So the problem he's looking at is this. You know, for wide area surveillance, the resolution cell is like 150 meter by 150 meter. The resolution cell is big because you're doing wide area surveillance. You're looking for a moving target like a tank or something, yeah? So, but then it's protected because tank compared to 150 by 150 meters is a little thing, right? It's protected by the stationary background, yeah? So this, if you want to know if this cell has a moving target or not, you need training data to do adaptive array. Yeah, you need snapshots. What do? You go to the adjacent range bins to find your training data. So a guy who came to you have to give a talk, he said, it's like you're looking for something in Taipei, you go to Kaohsiung to collect your training data, hoping that they have a same statistical property. That's hard to do, right? So anyways, so in his paper, what did he say? He said that, remember I don't have ensemble average, but I have sample covariance matrix. If my sample covariance matrix, right, the number of samples is 2 times of the dimension of the matrix, my SNR loss is within 3 dB. But a lot of people abuse his results. This is really nice seminal results, but people abuse it. Why? In his analysis, he's looking at this range cell. He's collecting data from other range cells. So your target, your signal of interest in this is in this range cell. It's not in the adjacent range cells. So that means this one here does not have your signal of interest. It does not have a desired signal. Your signal of interest is not in this data. Meaning this Q hat is an estimate of the interference and noise covariance matrix. It does not have your signal of interest in it. So this result only works like 3 dB loss if you have this one here 2 times the dimension of that one. Only works when this thing here does not have your signal of interest in it. If you have your signal of interest in it, big problem. Okay, the result does not hold at all. Like if this thing here has a signal of interest in it, if it's strong, T can be 10 times, 1,000 times a dimension. T, your sample snapshot number is 10 times, 1,000 times bigger than the dimension of your matrix, you still have your signal, desired signal getting suppressed. Because the signal is too strong. Remember, it's trying to kill the whatever, it's minimizing the very output power, right? If you're too strong, you stick out and then you get killed. That's the idea, yeah? So this theory does not work at all if X has your signal of interest in it, especially when your signal of interest is strong, okay? So we worked on this problem too. You see here, we published a lot of papers. I got a lot of citations. Okay, you should check the Google Scholar citation. This one has probably more than 2,000, but even close, I don't know, more than 2,000 total citations. This paper here. Okay, what's this? We worked on the Capon beamformer too, trying to make it robust. What happened is we're trying to say, remember that delta, gamma, whatever. We don't know how to choose them. We try to connect that uncertainty, that parameter, to the calibration error, your array calibration error. That's what the paper is all about. Okay, after all the work, turned out to be diagonal loading also. Okay, it turned out you still usually don't know how much calibration error you have for your array. Okay, so we wrote these papers here. You see a bunch of papers, right? And then we collected a bunch of people to do this edited book. This is edited book. It's much easier because we only need to write one chapter. Anyways, in this book, we are still in the Capon box. Right? We are still trying to make Capon robust. We are still in that box. So we wrote papers. We got highly cited. Why? Because array processing is so ubiquitous. You write a paper, it gets highly cited. Okay, we got more than 2,000 total citations for that one paper, right? Like some of my colleagues at UF, their total citation is 2,000. This one paper is more than 2,000 here, okay? But they are all limited. They are all still constrained to the Capon box, right? So they still suffer from the same problems, meaning they fail to work well when the desired signal is highly coherent with another signal, when you have few snapshot problems. They all need user parameters, which is hard to choose in practice. See, for our work, we need to know the array calibration error. Am I too fast, too slow? How's my... Huh? I'm fine, okay. So here's an example. Suppose I have two coherent signals. One is from theta 1, one is from theta 2. They are the same signal. What happens is when you have coherent signals, these two add together, right? Then this theorem vector here, does not correspond. You cannot find the theta so that these two add together is equal to some scaled version of a theta. Because it's two theorem vectors add together. It's not like equal to one of the thetas, right? So when you have two coherent signals, you use DBF, you get this black line. The two signals are close to each other. They are not resolved, right? But they are not killed either. You just get a big bump. When you use Capon, the red line, people will say, it's kind of working because you have a bump. Guess what? Because your signal has a steering vector now, it's this plus that. When you use Capon, it's killed. Both of your signals are killed. Okay? The reason you get a bump here is W is big, so you're magnifying the noise power. This red line is reflecting the noise power because your two desired signals are killed, right? Yeah, they don't work. So some people say, your Capon work. You see, you give me a bump. No, your two desired signals are completely killed by Capon's weight vector. Okay, only the noise is magnified. Anyways, so what happens is we've been working on this for a long time. Okay, and I gave one of my students, see here, this guy here, I gave him some ideas. Turned out to be later on called the iterative adaptive approach. Okay, and then because during the simulations he found the problem that he found some problems he was doing, and he's from best school called Bilkent University from Turkey. That's the best school in Turkey. Okay, and the English is much better. I was complaining about written English. His English is much better. So we made him the first author. Okay, published in 2010. Remember this date? Because the patent from Intel is 2020, a decade later, okay? Intel patented IIA, I tell you what, I'm going to tell you that, which is what motivated me to nominate myself to be an IEEE AESS distinguished lecturer, which is what made it possible for me to come to Taiwan again after 24 years. Anyways, so we published a bunch of papers on this topic, right? So this is the first IEEE AESS paper, and then this one here is related to like regularization for the IIA algorithm, okay? It's published, because this paper was accepted, and then from to appear, it was a long time. During the time we were writing more papers, that's why you see they were published in the same year, okay? But anyway, so this one is related to regularization. This is related to using it for space-time adaptive processing. And then this one here, that's this one, same guy here. He did a nice work here on doing fast implementation using Goldberg semantical factorization. Why? When you have a uniform linear array, the array covariance matrix is toplets. So if you explore that toplets structure, you can make it much faster. Guess what? Like within a month, I got an email from a guy. He said, I read your paper, okay? I could not make it work. Either you give me your code, or I give you my code and you debug for me. I did not reply that email. I'm not sure how to reply that email. Number one, the student graduated a long time ago. I don't have code. Number two, I don't want to debug his code. Anyways, so we read a bunch of papers. This guy here, he has a math degree from KTH, Royal Institute of Technology in Sweden. He got his PhD in applied math, but his topic is spectral estimation. So he worked for industry company, like insurance company for almost 2 years, right? Got bored. He wanted to come to academia again. So he decided to be my postdoc for almost 2 years. And then become faculty member at KTH again, Royal Institute of Technology in Stockholm, Sweden again. So after he got his job, he left me. And then 10 years later, I visited him again in 2023. In 2023, I visited him again in fall 2023. Guess what? In 10 years, he already became from assistant professor to full professor. And 2 kids, 1 son, 1 daughter. So I was laughing at him and I was like, Yuan, what did you do for the past 10 years? You are very productive. 2 children, and from assistant professor to full professor. But anyway, so when he was a postdoc, this is one of the papers he published. Also try to make IA fast when you have missing data, when it's not uniform linear array, when you have like sparse array kind of problems, okay? So what's the idea? I tell you what did I say? I said, IA overcome all of the limitations of the Capon family of beamformers. Seriously, I retain the merit of the Capon beamformer, including super resolution, including excellent interference rejection capability, and IA has now been used widely in practical applications. Seriously, it's becoming famous. Okay, I'm going to tell you more stories about that. So how does IA work? Here's the idea. Here's the trick. What I did was we divide the angle space for array processing an angle, right? Angle into grid. And the grid is fine grid. Because IA has high resolution, super resolution. Usually the grid size, if you use the 1905 beamformer, if the resolution is 10 degree, your grid size should be 1 or 2 degree, meaning 5 to 10 times finer than the standard beamformer because it's super resolution. Okay, any finer not needed. Why? I tell you the truth. This guy's resolution is about 2 times better than the 1905 beamformer. 2 times, not more. So, you know, you make it more finer, work harder, no use. In terms of resolution, no use. But besides resolution, side lobe is important, right? If your lobe is low, you have interference rejection capability, right? Side lobe is very important. The lower the side lobe, the better interference rejection capability. So this guy here has excellent side lobe suppression capability. I'm going to show you with the movies, little animation. Okay, so then what you do is, you have the grid, right? If you have something idea about how much power on each grid, you can form something called the fictitious array covariance matrix. So you see here, power, angle, from all these grids, I collect them all together into something. This is not the regular covariance matrix. It's called the fictitious covariance matrix. You know, I divide the thing into grid. I look at each grid, how much power, and then use that connect together, form this, add them all together, form this array covariance matrix. Because I want to know where power is. If I'm interested in this one here, if I'm interested in this one here, right? I want to, everybody else want to be suppressed, right? So I need to get an idea what the power is.
You consider a linear array?
Any array. Any arbitrary array.
But you have a G.
But this is angle. This is angle.
But SG bar stands for
signal at this angle.
That means you have G desired signal.
I have a huge number of signals. Because I divide the space into angle grid. Each grid, remember, it's 5 to 10 times bigger. If I have 10,
array is not linear, it's any shape.
My array is any shape.
Any shape.
This is
Only
angle.
one snapshot.
Only one snapshot. Arbitrary array, one snapshot. Okay. And my only requirement is you have a grid. You have to look at every grid. The grid is fine grid because I want to have super resolution, right? You don't want a too coarse grid. You miss something. Okay. All right. So you see, if I know the signal, I know the power, right? And I want to know how power is distributed over angle, and then I use that to form this fictitious covariance matrix. Once I have that, you see, this is basically like Capon, same math for Capon, right? The R, remember the trouble R, is now replaced by R tilde, the fictitious covariance matrix. Okay? And then you're going to ask me, how do you know power? How do you know power? How power distributes with angle, right? You want to ask me, you don't know how power distributes with angle. So how do you know? Well, that's where iteration comes from. And through iteration, I learned that. See, I'm not very good at calling names for my algorithms. I just say it's iterative, it's adaptive, it's an algorithm, it's an approach. If you do machine learning, support vector machine. What a wonderful name, right? I should call my algorithm some kind of machine. Right? The support vector machine is a machine.
It seems to me you don't have objective function. Your array output minimizes
If I know the array, fictitious array covariance matrix, right? My problem becomes that Capon's problem. So that's the optimization problem. That Capon, Capon, remember, it needs R, right? I don't have R, I give R tilde, and then use it like Capon. The problem is, I have to do iteration. And then you say, okay, iteration is fine. Maybe you can do iteration. Then, right? Iteration means, you find your R tilde from previous iteration. Yeah? You find your signal, form this, and then use this to replace that, and then do iteration. So you find your R tilde, you update your signal, and then you update the power, update the R tilde, and then do it again and again. That's the iteration. Fine. How do you initialize your algorithm? Remember, I already planted a seed. I said, I'm a fan of Karl Braun. So I initialized with Karl Braun beamformer. It turned out that this algorithm is robust too, because this first step is Karl Braun. Yeah? Another thing is, another wonderful thing is this. You know, A is all assumed steering vector, right? I don't know the true steering vector. We don't know. We don't know how we calibrate the array, how fine or exactly, right? Environment changes, summer, winter, maybe array calibration error is all different. So I don't know exactly, right? However, whatever I assumed, I use it to form fictitious covariance matrix. So the A here and the A inside here are the same. So I do not have signal cancellation problem. Remember, it's A, assume the true A different. You have cancellation problem, right? My R2D used the assumed steering vector. So assume here, they match each other, they don't cancel each other. I have robustness problem too. I'm going to show you with pictures, with the results.
So it is a greedy algorithm because you have to roll over the OG grid to
Right. It's not greedy. It's not sparse. The spectrum from IEEE is not sparse. It's not a sparse algorithm. So it's not a number of compressive sensing algorithm. Seriously. It's not sparse. It's robust. It's less, you know, I have some other algorithm I'm going to talk about. Okay? They are more sparse. When you sparse, you tend to have biased underestimates for power. Meaning your power estimates are smaller than the true value usually. The sparser algorithm, the more biased under somehow. For some of my algorithms. I have sparse algorithm too. Okay? They are more sensitive to signal to noise ratio. They are more sensitive to a lot of things. So this one here is not sparse. Its resolution is not as good. It's only 2 times the Braun resolution. A factor of 2 improvement, no more. Some of the sparse algorithms, like Slim I have, are much better than the resolution, but they're more sensitive. And also, you know, it's also iterative, right? Sometimes after 3 iterations, it starts to go bad. This one doesn't. I'm going to show you. So this one is not sparse, it's robust. Just look at the results, okay?
Excuse me, so simply use the Capon as the initialization value.
Not Capon. 1905, Karl Braun.
Capon.
Yes.
So
Okay.
we simply use the, in my field, we call delay sum beamformer.
Delay sum. It's exactly delay sum. Because for phase array narrowband signal, delay means phase change.
So you use delay sum beamformer to guess, to do the initial guess of the power.
How power distributes over angle.
Okay.
Now, how IEEE is going to be applied to wideband signals, that's a research topic. How do you do it nicely? That's a research topic. I haven't done that. I'm busy marketing this one. Anyway, okay, let's do a simulation, okay? 10-element array, right? The resolution for 1905 Karl Braun beamformer is 10 degrees. I have 2 signals. I think they are spaced 5 degrees apart. So basically, if you apply the 1905 thing, you don't see 2 peaks, right? They are within 1 beam. You're going to see a big fat 1 peak, yeah? Okay. Here, ideal Capon means you have infinite snapshot, you have signals completely uncorrelated, you have no array calibration error. When that happens, you use Capon, you get this black curve. Nice, right? Super resolution. Look at the side lobe level. You have 10-element array, 20 SNR, because array gain is 10 dB. So if your signal is 0 dB, that means noise is minus 30 dB. You see? All your other signals, no side lobe, is suppressed to noise level, no side lobe. This 30 dB is noise. Why noise? You can't do lower than that. See, incoming SNR is 20 dB, array gain 10 dB, so your noise level is 30 dB, right? At minus 30, right? You can't do better than this, okay? All right, so that's the ideal Capon. Now let's only take one single snapshot. That's the red curve. See, IA inherited nice super resolution property, works for single snapshots. Okay? Reduce the interference to almost like a noise level. You see here, it's a little bit above that, right? But much lower. The side lobe level is much lower than 1905. Okay. I'm going to show you more examples.
For this, the clinical resolution for the previous slides is much in your snapshot the angle resolution.
So the angle resolution for 1905 algorithm is 10 degree, right? For IA it's 5 degree. 5 degree. Easily resolve them. Right. You can make them closer, then you're going to have like the peak is like the middle part is shallower. So this part here becomes shallower, and you move the two together. Okay? And then this area here still looks nice. This area here still looks nice. Oh.
You assume that also you tested for +5 and -5. The two.
Yeah. I think it's
5 or 6.
I don't know. Maybe if that's 20, that's 10 degree. That's 10 degree. But anyway, if you use the 1905 one, because it's 3 dB, the resolution is 10 degree. You're separating by 20 degree. You probably can see two peaks, but it's like this. Barely see it. Right? You are at the resolution limit. You are at the limit. Smaller than that, you don't see it reliably. But look at this. No question, two signals, right? Deep knobs in between, yeah?
Then my next question is you are using this test, but two samples separated by 10 degree, but it's -2.5 and 7.5. Does it still result like this?
Stay tuned.
Okay.
Look at this one. This should be a movie you should play like animation. So this is a sparse array. This is a sparse array. 10 elements, but look at the wavelength. It's a sparse stretch, right? Sparse array has a problem. Oh, it's not playing? Oh yeah, it's playing. I know it plays. Because I emailed the PPT, right? Look at the resolution. Did you see that? Did you see that? So 0 means the 1905 beamformer, right? Very high side lobe. Because sparse array, the side lobe is more than -13 dB, yeah? Higher. You see how high it is? You almost think these are fake targets, right?
Iteration 0.
Yeah, that's the 1905. Iteration 0 means initialization. I used the Braun beamformer, DBF, to get an initial idea how power distributes over frequency, over angle. Angle frequency is the same thing, spatial frequency is angle, right? And then look at the iteration. Did I resolve them? That answers your question, yeah? You see, the two are separated by 1.5 degrees for sparse array. The DBF cannot resolve it, right? You only see one peak. Look at how I resolved it. So the closer they are, the shallower the middle part of the peak. So how deep depends on your problem. And also how the two signals are related to each other sometimes. How the phases of the two signals are related to each other. It's kind of related to that too somehow. But 10 iteration. Maybe I'll do this. I'll try this. Because I forget. I think I got it. Okay. Can you hear me?
Yes.
Okay. 10 iterations. What did I do? What did I do? I reviewed too much secrets. So 10 iterations. Basically, it doesn't change anymore. So I can't prove convergence, but empirical experience says 10 iterations, basically you are guaranteed with probability very close to 1 that it's going to converge. It doesn't change anymore. Just don't do more than 10 iterations. So high resolution, low side lobe. So the biggest advantage, the resolution is a factor of 2, right? That saves you a lot of money too, right, already. And the silo part saved you a lot of trouble. Why? That's interference suppression capability. Very good interference suppression capability. Yeah? And also 10-element array, SNR 20 dB, your noise level should be at minus 30 dB. Look at what it's doing. It's basically killed here. Right? The two close, they're so close that the number is not big. That's what you're going to see. The closer they are, the smaller, the shallower the valley between them. But for other guys here, really killed them. Yeah. So what did I say here? The single snapshot eye offers super resolution, significantly reduced silo area. By the way, if you have a single snapshot, do you still need to talk about the two signals being coherent or not? Not really. Because if the two incident signals are coherent or not, it's related to temporal. You have to have a waveform, it's multipath, right? They are coherent or not. But when you have only single snapshot, two numbers, what do you mean? Correlation or not is meaningless. It's out of the window, right? So it works for coherent, uncorrelated, coherent, partially correlated, anything. Because it works for a single snapshot. Any questions? Okay. Professor Storker, my longtime collaborator, he's basically, in my mind, an applied mathematician. His math is from Romania, right? He's in Sweden. He's an international member of U.S. Academy of Engineering and also Royal Swedish. He's basically Academy membership, 5 Academy membership. Okay. We have a paper, he's first author. Okay, that means he did most work, right? That's published in, this is a very good paper actually. It's published in Digital Signal Processing. This paper was submitted to IEEE Signal Processing magazine, was rejected. So we sent it to here. But it's really a good paper. In this paper, it's called weighted spice. So it's using an umbrella to unify a bunch of algorithms, including IA, including spice, slim, likes. Okay? They have different properties. But I remember he came to my office one day because he was visiting University of Florida. He said, you know, we tried, this was his postdoc, right? Dave Zachariah. He tried many simulations. IA is the most accurate. No matter what he does, he can't beat IA. Okay, I think this is really a paper that's, even though it's in this journal, right, it's really worth reading. Okay? Anyways. So this is umbrella, right, unifying all these algorithms. Some of them are really sparse, okay, but not robust. All right, so in 2020, this paper, in 2020, he and his co-authors, right, wrote a paper in IEEE Signal Processing magazine. You remember our paper was rejected and was published in the ESPRIT, but their paper was published here in 2020, right? So if automotive radar, radar is useful for autonomous driving because it's all weather, day and night, okay? But they like 1 degree resolution actually, so it's still a challenge, right? Anyway, so in this 2020 paper, in this magazine, they compare IA with a bunch of other algorithms, okay? He's a membership of both Academy of Engineering and Academy of Science. Okay. So in this paper, you know what he did? He said this. If you are a practitioner, what do you want? You want a reliable algorithm, right? So you want to look at the robustness to be strong, right? The two algorithms that got the strong robustness, one is 1905. Karl Braun beamformer. The other one, which is used to initialize this one, the other one is IA. Low resolution, super resolution, works for single snapshot. This one too, right? Because it's data independent. Any array, yeah. This one here, did you notice that when we do this, we don't have any user parameter. There's no sigma, delta, gamma, something to tune. Very easy to use. Just use it. So there's a guy, he is with University of Australia, University of Newcastle. He said, I apply to any data I can get my hand on. I never disappointed me. That's what he said. Okay? And you see the famous algorithm music, ESPRIT. You see the sensitivity, right? Orthogonal matching pursuit, that's a greedy algorithm. Orthogonal matching pursuit, orthogonal matching pursuit. You see that? Okay? Orthogonal matching pursuit, it says resolution high. I disagree. Orthogonal matching pursuit is a variation of matching pursuit. Matching pursuit is basically a reinvention of a clean algorithm in 1974. Clean, C-L-E-A-N, in the Astrophysics Journal. Okay, it's a reinvention. So clean is not super resolution, then MP is not. OMP is just a simple variation of MP, so it's not super resolution at all. Anyways, so I came up with some simulations just to show you, for a weird case, how IA performs, how music, ESPRIT, OMP performs. Okay, so in this simulation here, my signal is a distributed source. Why? Look at the angle. This is the angle, right? The true one is a rectangular pulse. So basically in time domain, if you look at time domain, it's a sinc function, right? Sinc function, rectangular pulse in the angle domain, spatial frequency domain. So this is dBF. This is you see, very robust, right? Nothing changed. They're almost the same. Okay? But IA is much better than dBF in many ways. For example, silo much lower. Weak target detection capability much stronger. Interference rejection capability, because silo level very much stronger, right? Look at this example here. I have a signal here, yeah? I have another signal way down here. Okay? That happens in autonomous driving. Why? Because the reflection from a semi-truck, big truck, is much, much stronger than the child, right? Than the little animal, whatever. 60 dB is stronger, probably more, yeah? So that's like this case here, similar to this case. One strong, one weak, yeah? If you apply dBF 1905 algorithm, strong robustness, right? You get the black curve. What happened to the weak one? You don't even see it. It's totally buried by the high side lobes. Because it's so much weaker, right? It's much weaker than not only the biggest side lobe, the second biggest side, the third biggest side lobe. So you don't almost see it, right? Look at IA. IA is red curve. Single snapshot, yeah? IA is red curve. You see nice, you see how accurately IA estimates the power? You see nice, yeah? Two targets clearly, right?
So for this case, why side lobe can be minus 70 dB?
That's related to SNR, signal to noise ratio. Signal to noise ratio. Meaning this guy here, the signal to noise ratio, right? This guy's signal to noise ratio is like 70 dB. This guy's signal to noise, after beamforming, this guy's signal to noise ratio is, I don't know, the difference between here and here. Minus 45, so 25 dB. So your weak target, even though it's much weaker than the strong one, is still stronger than the noise. If it's weaker than the noise, then they are in trouble. It's buried by noise.
Still you're using 10
Right, SNR. So 10 element array means array gain is 10 dB. Array gain is 10 dB. So if your input is minus 60, now it's minus 70. Yeah? So the noise is minus 60. So the weak signal, this is to show you strong signal, weak signal, but the weak signal is still stronger than the noise. If it's weaker than the noise, you're dead. You can't do anything about it, right? If it's weaker than the noise after beamforming, then it's buried by the noise. You don't see it, period. So to see it, you have to be stronger than the noise. Okay, so this is a very interesting case, right? Side lobe is really, really important when you have a the communication guy called it near-far problem for CDMA, right? It's kind of near-far problem, right? Big target, small target problem. Okay, so compared to music, ESPRIT, that's famous Star Wars algorithms, right? Subspace algorithms. You see, they require ULA. They require a lot of snapshots or ULA. You know, you need to rank. You need to know the rank. Basically, you need to know the number of signals, something like that. That's user parameter. Again, trouble, right? And your robustness is medium. Okay, let's see how they perform. This is how music performs for this. Not very well, right? Okay. This is a small attack on the parametric algorithms. So basically, DBF is here. Nonparametric, very robust. Subspace methods, maximum likelihood is way here. Okay? Parametric can be good if your model is correct. Yeah? But sensitive, right? IA is here. Okay? IA is here. And it's good to use, no user parameter. And OMP is a compressive sensing algorithm. Let's see how it performs. This is OMP. Okay, now what motivated me to give this talk is this patent. Intel patent. These guys here, I used to be with Mobileye. What's Mobileye? You know that. You should know, some of you should know that. Mobileye do the software for autonomous driving. At first, they do it for the cameras. And then they included the radar. And then they discovered the IA algorithm is really good. So they decided to patent it. Okay? They didn't even bother to change the name. Why? Beamforming techniques implementing the iterative adaptive algorithm. I'm going to tell you what's in it. Okay. In this patent here, they also mentioned our previous. You know, we don't come up with IA like overnight. So we have previous versions trying to get that, right? So we have an algorithm called APES, APES. This hasn't even mentioned that algorithm. Also called it APES. Okay? Why do we call that algorithm APES, APES? Because we think all other people's algorithms are monkeys. But anyway, at that time we thought APS is much better, right? IA is much better than APES. IA is much better than APES. Okay? But at that time we thought APES is pretty good already. Anyway, okay. What troubles me is this. This patent did not mention any of our papers. Did not reference any of our papers. Zero, nothing, none. Okay? They have basically said, oh, IA is kind of slow. I'm going to explain to you why IA is slow. That's why, you know, we need the couplets thing to speed up kind of thing. Yeah? And why it's slow, where it's slow. But anyway, so they came up with some algorithm to reduce complexity. One is called reduce complexity IA. We tried it, doesn't work very well. Okay? And the other one is called, it's really a bad name. BS. Okay? BS. Beam space. You know, we were like, we use it all the time. We use IA to form a radar image for a car, right? Usually the image is big, yeah? So that means the data is really big. You stack the 2D data into 1D, it's big, right? Then you need matrix inversion, R inverse kind of thing. It's computation costly, right? So you know what we do? We use FFT to get the image, initial image, right? We see where the car is, we actually take a hole out of it. Sometimes we do Windows FFT, take a hole out of it, yeah? And then go back to the data, phase array history. It's called, in radar terminology, it's called phase history data. So when your image is this big, but you took out only this piece, go back, it's this much data. So computation is much faster, right? We do it all the time. That's what this patent is. We're like, what? This one doesn't work. This PSI is basically what we do all the time. You use the FFT or window FFT, go to the domain, pick out the area, go back. If you use window, you de-window it when you go back.
From M space to B space to apply the IEEE.
Basically, that's the idea. Beam space, right? Basically, you know, you go there, you find, oh, this area you are interested in. That's beam space, right? You take that thing and go back. Then you have smaller data. So it used to be 1,000 elements, you need to do 1,000 by 1,000 matrix inverse. Now you only need to do 100 by 100 matrix inverse, right? If that's the idea. That's the idea, total idea. Okay. Now, why is it Intel patent? Because Intel bought Mobileye. Mobileye is this company here in Israel. Did you see this? Yeah. So Mobileye. These are all Mobileye people. It's called Intel patent because Intel bought them. I think there's some trouble. Later I read that Intel bought Mobileye, and then they sold Mobileye again or something. I don't know. I didn't pay attention, but I was looking at this. I'm like, I need to do something. What can I do? So I decided to give you lectures talking about it. Okay. Actually, another story is this. I received an email from a company called DBS Radar. It's used to be RADA. That company is called RADA, Radar. And then it's now combined with or bought by another company called DBF, something, 3 letters, Radar. Their director of innovation and research wrote to me. He said, oh, I listened to your distributed lecture. This is the webinar. You can find it online. This electronic version can be found online because in March I think 15th. In March 2023 I gave this talk, first time. And it's online. It's an IEEE webinar. You can Google it. And he said, I listened to that. I'll implement your IA algorithm. It doesn't work. And I said, because there are common mistakes, right? I said, did you grade the angle from minus 90 to 90 degrees? If you only grade, for example, the angle from minus 45 to 45 degrees, you are leaving this whole area uncontrolled. You can go crazy. So I said, did you do that? Did you do this? Did you do that? Did you do that? He came back. It works fine. And then he said, I truly admire your work. To me, that's like, being professor for your whole life, right? Somebody in practice, in Israel, trying to build the Iron Dome to protect themselves, to say that I truly admire your work. To me, that's like a reward. Another thing is this. In DARPA, Frank Roby, he's a DARPA program manager. He started this program called BLIP. The name is a little bit too transient, BLIP. But it stands for this. And look at this. They're trying to do this here. Okay. They want to look at the feasibility. Is direct what general radar needs with a view to demonstrating feasibility and practicality of nonlinear and iterative signal processing. Okay. So they are kind of interested in this kind of thing too. So, iterative algorithms is not limited to IA. I told you Slim, Likes, Spice, they're all iterative. But they all have small differences. Somehow that small differences makes them have very different sparsity properties, different resolution properties, different robustness properties. It's in that DSP paper, remember that the one that was rejected and then published in DSP? It was all in that, to show that, with simulations and a lot of theory. Okay? So small changes somehow make a big difference. And this is interesting, right? I don't know if it's related to me giving this talk all over the place. I went to KTH to give this talk. I gave this talk in KAIST, Korean Advanced Institute of Science and Technology, Chinese University of Hong Kong, whatever. Also on the webinar. Now it made matter. The function is called IADOA. You see in the array processing toolbox. starting in 2024. So if you don't want to code it yourself, you can use it. But it's not a fast implementation. Remember the guy wanted me to debug for him? I did not reply his email. What would you do if somebody asked you to debug his code? Somebody you don't know? What would you do? Professor Chi, what would you do? That's it. I think did I overkill my time? Did I talk too long? 5.
Okay, then switch to the right.
Excuse me. So the patent granted?
Oh yeah, that's a patent. Its valid date is that.
If the application is A1,
Huh?
its application of the patent application is not granted.
It's granted.
Granted.
It's granted. United States patent publication. It's granted. Published on April 30th, 2020. That's a patent.
The process is not yet granted. Based on this feature, it's not yet granted. Maybe there's some question or problem.
The extension A1 means
A1 means what?
It's still under application.
Oh, I hope then all my lectures killed it.
Okay. Got it.
And this company is very eager. They fired in December 2019, but they published it, they voluntarily published it 4 months later, so they are very eager to.
Oh, you see, you guys are better expert than me looking at the patent.
It's not yet granted. Maybe a few of you reject or.
Hopefully I killed it fast enough. Because the first talk I gave was in March 2023. I don't like it. I mean, you do this, right? You don't cite our work. How could you do that? I don't know.
I don't think they try to patent. They simply try to avoid somebody patent.
Really?
Yeah, that's the way how they. I think that's the way why they try to patent. Once they file the patent applications, that means it's open.
Right.
So nobody can file the same patent.
Okay.
The good news is they are trying to use this in their product.
But they didn't cite any of our work. Would you have a problem with it? I don't know. Anyway, but I'm also on the other hand very happy that people in practice, the practitioners, like it. I'm very happy that the practitioners like it. Now, I want to give you shortcomings. There are shortcomings with this algorithm. This one here, this is the bottleneck, computational. Because for every grid point, you have to calculate this. It's computationally much more expensive than the 1905 algorithm. So there's no free lunch, sorry. So if you are smart, you probably can make it really fast, much faster. Real-time implementation, whatever. So there are still room to grow on this topic.
Okay, then it has been 100 years, so we're still moving forward.
It needs to be faster, for example. That's one of the possible topics. So as long as you have an array problem, you are going to run into these things.
Does this would apply to another array structure like hybrid structure or other array structure? Apply to such an array structure like hybrid array. Hybrid array.
What's a hybrid array?
Hybrid array. Less live chain and more
Combining digital information and
analog.
So you have maybe some analog processes and some digital processes to combine together.
Hybrid.
Hybrid beamformer. Hybrid beamformer. Hybrid array.
I don't usually think from the hybrid angle, so I'm not sure. I don't know, maybe somebody else is doing it.
Digital beamforming and analog beamforming.
Analog beamformers. The
Hybrid.
hybrid is
Both.
part of, that's, the purpose is to reduce cost,
Reduce the hardware cost.
hardware cost.
It's like you perform analog beamformer first, and then you can reduce the channel count. So once the channel count is reduced, then you perform the digitalization and then perform the digital beamforming. Is that?
Then basically you can do that after you reduce the channel count. Then you can apply, and that's faster, right? Much faster.
Hey, Janet, wireless communication, they are hybrids, remote operation, digital beamforming, analog beamforming.
Right. So if you do analog and then you reduce, then you basically apply IA here, which is nice, right? You reduce your computation greatly. Because our inverse is like third power, ON3 computation, right? 3 times computation.
Now the computation cost for this is not, it can be done in parallel.
Yeah, you see here? All of this.
Yeah, because it's pixel by pixel based, so you can separate pixel by pixel for parallel computing.
Grid point.
Yes.
All of the grid point you can do in parallel together. But then it's hardware cost. You do parallel processing, you have real-time implementation, but then you have hardware cost. And also, even during the parallel implementation, do they need to talk to each other or something? I don't know.
Yeah, for GPU implementations, they almost no cost. Nowadays.
Really?
Yeah.
Really? That'd be good news, right? But there's still room to go to do things to do.
Any more questions?
So, in addition to the computational capacity or the computational cost, what else the drawback you think they're coming from the IEEE?
Computation?
In addition to the computational cost, what else is the disadvantage from IEEE?
Mainly is that you need to calculate this for all of it.
Yeah, but you kind of using the
And then
bin space to approximate the channel domain data. So in that case, what if the bin space is quite different from the channel domain data? What would happen? For original component, people using channel domain data to estimate the covariance matrix, right? But now you're using bin domain data to estimate the power of
right, fictitious. Yeah, it's a fictitious.
Yeah, so what if the bin domain data is quite different from channel domain data? That means in that case, your method may fail, right?
This is from Braun. Braun's method is reliable. So you start from reliable, you're doing small iteration learning. Usually it doesn't go crazy. They do not go crazy. We have not, like the professor from Newcastle, he said he tried the IA for any data, all the data he can get his hands on. I never failed him.
So did you prove it must converge? Did you prove it?
No theoretical proof.
Okay.
There's a guy who attacked me. He said, "Oh, this algorithm is simple. Look at it. It's just a matrix inverse. It doesn't have differential geometry. It doesn't have fancy mathematics." I'm like, FFT is simple too. It works. So this works. No proof of convergence. Maybe you can also do it. Seriously. Okay, no proof of convergence. Computation is slow. But if you can do something, you can speed it up. Like when you apply to 2D, you have to stack your data together, right? You get out of control your dimension, get out of control very quickly, right? From n something to n squared.
Maybe add some more considerations, some constraints, or some
Professor Tony Chen is hardest trying to keep this out.
Congratulations.
Which is why you wrote that, yeah.
So I have one question. So it seems that it's still limited to 2D. So is it possible to extend to 3D?
Probably just computation. Think about if your data is n, right? 2D is n squared. That computation is dimension, your data dimension is n squared. 3D is n cubed. Your matrix size is n cubed.
Besides complexity, this algorithm can be extended to 3D.
Theoretically, why not? You just need a lot of grid point. It's a voxel, right? The number is big. But I think it's doable. Yeah.
Okay. Very good. Any more questions? Okay, I have a couple of questions. 6G radar sensing. Those nice work. IEEE radar sensors is going one of the 6G topics.
Yeah, called
IESS.
joint
Integrated.
Integrated sensing and communication.
Are you working on that topic? You are? It's an interesting area, right?
Then, well, seems something can be done for 6G, integrated sensing and communications. If IAA can be applied, that would be excellent.
Right. But as long as you have an array processing problem, IA should be considered. Karl Braun should be considered. Delay and sum, right? Delay and sum should be considered. Karl Braun should be considered. IA should be considered. And also always use Karl Braun method as your benchmark. Here's the least I can do.
And they use it in non-linear processes, AI. The AI is a non-linear.
Right.
Then 6G also, I believe AI will do it in some way.
Right.
Then non-linear processing. IAA, is it possible involving AI?
The guy, this guy here, this guy, he's now University of Alabama professor, Tuscaloosa campus. He's a fan of IA. He's been trying to involve me in some of the machine learning realization of IA algorithms, some papers. But I want to confess, I don't know too much about machine learning.
Okay. Any more questions? If no more questions, that's